In this second film on the laws of motion, we're going to start with the air track again. The two gliders have magnets at one end, with light poles outwards, so that they repel each other. The counters time the passing of the known length of tape in 1/20th of a second, thus giving a measure of its speed. We're going to investigate what are called elastic collisions between the gliders, and use the counters to compare the speeds of the two bodies. Watch again. The moving glider stops dead. The other one moves off with exactly the same speed as the one which pushed it. We're observing the conservation of momentum again. The first glider transfers all its momentum to the second. Exactly the same speeds, again. Now we're going to take two exactly similar gliders as before, but instead of a magnet, each has a lump of plasticine at one end. When these collide, they'll stick together. We'll get what's called an inelastic collision. Here's what happens. Now the first glider has a strip of white tape as usual, so that we can see how long it takes to pass beneath the detector, measured in 1/20th of a second. There's the plasticine. The glider with which it collides has no tape on top. So the second timer will measure the time taken by the same length of tape passing by. Let's carry out a run. The double glider moves off at half the speed of the one that collides with it. The tape takes twice as long to pass the detector. Another run, the single glider taking this time. And the double glider takes almost twice as long, half the speed within the experimental error. A slower one. Once more, the two gliders, double the mass of one, move off at about half the speed. This is another instance of the conservation of momentum. We can apply the law of conservation of momentum to measuring the speed of a rifle bullet. In fact, we'll use an air gun and find out the muzzle velocity of the slugs it fires. We have to weigh each slug. The actual masses are given in the Physics in Action booklet. And we have to weigh the glider, which has a tube stuffed with wadding fastened to it to act as a target. Again, the mass is in the booklet. There's a strip of white tape on top to activate the detector, and we need to know the length of this. Once again, it's given in the Physics in Action booklet. We fire a weighed pellet at the target. And note the time, measured in 20ths of a second again, which it takes for the length of tape to pass. From this, we can work out the speed of the glider with the pellet embedded in it. Another shot with another weighed slug. We know the masses of the pellets and the glider and target. You can use the principle of conservation of momentum to calculate the speed of the pellet when you've worked out the speed of the glider plus target from these timings. Pouring liquid nitrogen into a laboratory rocket. We're going to see how Newton's second law of motion applies to the behavior of a rocket, the action of a constant force producing a constant acceleration. When we've jammed in the cork, a stream of nitrogen gas will emerge at the jet from the boiling liquid inside and propel the rocket forward. You can see it accelerating. We weigh the rocket. It weighs 1,500 grams. Now we're going to measure how far the rocket has travelled at 2-second intervals using the scale on the air track, from left to right this time.
Start. Mark. 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 Mark.
Now let's look at the distances. You can write these down if you want to take part in the experiment. The rocket started here on the scale at 70 centimetres. After 2 seconds, it reached here, 80.5 centimetres. After 4 seconds, here. After 6 seconds, and after 8 seconds. If you plot the distance travelled in time t against t squared, you should get a straight line from the second law of motion. From the slope of the line, you can work out the rocket's acceleration. The nitrogen gas boiling off and passing out through the jet must produce a constant force if it produces a constant acceleration. Here's a rather crude way of showing that the force is constant, using a spring balance. The rocket pulls against the spring. It does exert a constant force, equivalent to about 6.5 grams weight. You can also calculate this force from the known mass of the rocket and its measured acceleration. The Physics in Action booklet has notes on this. The laws of motion apply just as much to the huge rockets used in space research as to this simple example in the laboratory. Newton's laws apply to all moving bodies of any kind, anywhere. The force of gravity causes falling objects to accelerate. The acceleration is the same, whatever the mass of the falling object. Let's compare the behavior of a feather and a much heavier metal washer. The feather has a tiny bit of metal wire fixed to it for the next experiment. But in air, it still takes longer to fall to the ground than the washer, because of air resistance. But suppose we drop the two in a vacuum. This pump's removed nearly all the air from two long vertical glass tubes. The washer and feather are held at the top by an electromagnet. That's the reason for the bit of wire on the feather. We'll let them drop. They hit the bottom at the same time. The wire gauze on the right is to stop the washer bouncing against the glass and cracking it. In case you didn't believe that, here we are again. And we'll stop the action so that we can see what's happening. They're practically neck and neck. If the objects are heavy enough, we can ignore air resistance. And if we drop these two balls, for example, they hit the ground at the same time. But suppose we drop one while trying to throw the other in a straight line parallel to the ground. It won't travel straight, of course, because gravity will accelerate it downwards, and it will actually hit the ground at the same time as the dropped one. There. This may surprise you, but it's true. The two balls, one just dropped, the other projected in a straight line, will accelerate downwards under the influence of gravity at exactly the same rate, and always find themselves at the same level at a given moment. If the aim's right and they don't hit the ground first, they'll collide like this. We're going to demonstrate that this is true using a special crossbow aimed at a target dead level with it up here. The target is about 15 meters away from the crossbow, across a big lecture room. We're going to fire this steel bolt at the target. When it's loaded onto the crossbow, it makes an electrical contact between two metal terminals. This means that current flows and passes along wires to an electromagnet which is holding the target in position. When it's fired, the connection is broken. The electromagnet is switched off and the target will fall. The targets are balloons filled with water, with metal attachments so that they're held by the electromagnet. We have to be sure that the crossbow is aiming straight at the target, and we use a laser for this. The spirit level shows us that the device is truly horizontal. The red spot from the laser must fall where the head of the bolt will be. The lining up must be absolutely precise. And now we know that the crossbow is aimed straight at the balloon.
Righto.
We'll try 4 shots. Here's the first. Well, it missed, but only just. Look at it again, and we'll slow down the action as the bolt arrives on target. Did you see how close that was? We don't always get a direct hit, because the bolt may yaw a little as it travels. We can't be completely sure that it will always move on the planned path. Let's try again. Was that a hit? Again, in slow motion. Yes. Now for shot number 3. It looked like another near miss. We mustn't put any sort of flight feathers on the bolt, like a dart. This would spoil the experiment. Can you see why? Anyway, it was very nearly a hit. Now for the last shot. A hit, do you think? Slow motion will show us. Yes. The moving projectile has fallen, accelerated downwards, at the same rate as the dropped balloon full of water. Let's go back to the drawing of a ball being thrown. With a certain effort, it travels this far before hitting the ground. Throw harder, and the ball travels even further before it hits the earth. If he could throw really hard, imagine he's some kind of giant Superman, this is what would happen. The ball would go on falling round and round the curve of the Earth, assuming it was outside the atmosphere so that there was no friction to slow it down. This is what happens when we send a spacecraft into orbit around the Earth, only we use the force of a chemical rocket to send it on its way. And spaceflight depends upon the scientists and engineers understanding the laws of motion and applying them to their rocket launchers and space capsules. When man sends a spacecraft into outer space to explore other parts of our solar system, everything depends upon a knowledge of chemistry to fire the rockets and of physics to guide it on its way. His calculations have to take account of the laws we've been exploring in these two films. Without an understanding of the laws of motion, none of this could be achieved. And the movements of the planets themselves and their many moons are also subject to exactly the same laws. Whatever the composition of Saturn's rings, for instance, however many other bodies circle the planet, they're all moving in obedience to the principles of force and mass and acceleration and momentum, which we've seen and tested out on our laboratory air track. The spacecraft goes on moving uniformly through space until some other force acts on it. Maybe a force which we'll activate from here on Earth, when we send out electromagnetic radio waves to signal the firing of a retro rocket, or the movement of part of its recording gear. These are physicists in action, using the ideas of physics to make space exploration possible. The motions of the planets and their satellites, the flight of a spaceship or a projectile, the behavior of a motor car or a football, these are all governed by the laws first discovered by Isaac Newton in the 17th century. Today, those same laws are still amongst the most important and useful ideas in physics.